Last time we found that training AI means minimizing a loss function. We had a beautiful bowl-shaped surface, and we needed to find the bottom. Today we're going to zoom in on the algorithm that does exactly that, gradient descent. It's the engine behind every AI model ever trained. Imagine you're blindfolded on a hilly landscape. You can't see the lowest point, but you can feel the slope under your feet. What do? You take a step in the steepest downhill direction. Then you feel the slope again. Take another step. Repeat. That's gradient descent. Let's make this precise. Our loss function L depends on two parameters, W and B. The gradient is a vector of partial derivatives. The partial derivative of L with respect to W tells you, if I nudge W by a tiny amount, how much does the loss change? Same for B. Together they form a vector that points in the direction of steepest descent. So we go the opposite way. The update rule is beautifully simple. New W equals old W minus alpha times the partial derivative. New B equals old B minus alpha times its partial derivative. That minus sign is everything. It flips ascent into descent. And alpha, the learning rate, controls how big each step is. The learning rate is the most important hyperparameter in all of machine learning. Too small, and you'll take thousands of tiny steps. You'll get there eventually, but it'll take forever. Too large, and you overshoot the minimum, bouncing back and forth, maybe even diverging to infinity just right, and you converge smoothly to the minimum in a reasonable number of steps. Let's watch gradient descent solve a real problem. Here's our data, house sizes and prices. We start with a random line. The loss is huge. Now watch. Step 1. The gradient tells us to increase W and decrease B. The line tilts. The loss drops. Step after step, the line fits the data better. The loss keeps falling. After about 50 steps, we found the best line. Gradient descent just learned from data. Now here's where it gets interesting. Our loss surface was a nice bowl. One minimum, easy to find. But real AI models have loss surfaces that look like mountain ranges. Multiple valleys, saddle points, flat plateaus. Gradient descent can get stuck in a local minimum, a valley that's not the deepest one. It can slow down on plateaus. It can oscillate around saddle points. So how do modern AI systems deal with this? Two key ideas. First, momentum. Instead of just following the current gradient, you accumulate velocity, like a ball rolling downhill. This helps you blast through local minima and plateaus. Second, adaptive learning rates. The Atom optimizer, used in almost every modern AI system, gives each parameter its own learning rate that adapts over time. Parameters that rarely update get bigger steps. Parameters that update often get smaller steps. Atom combines momentum with adaptive rates, and it's why we can train billion-parameter models. One more crucial idea. In practice, you don't compute the gradient on all your data at once. If you have millions of training examples, that's too expensive. Instead, you pick a random small batch, say 32 examples, compute the gradient on that batch, and update. Then pick another batch. This is called Stochastic Gradient Descent, or SGD. The gradient is noisy. It doesn't point exactly downhill, but that noise is actually helpful. It helps escape local minima, like random vibrations helping a ball escape a shallow valley. Let's zoom out. Every time ChatGPT generates a word, every time Stable Diffusion creates an image, every time a self-driving car recognizes a pedestrian, the model behind it was trained with gradient descent, billions of parameters, updated millions of times, using the exact same update rule we just learned. W gets W minus alpha times the gradient. That's it. Next time, we'll look at what happens when you stack many linear functions together, and why adding one simple trick creates neural networks. If this helped you understand something new, subscribe. See you in the next one.